Okay, so in the about half an hour which we have remaining, let us do some tutorial which we intended to do. So this is the first tutorial for this course, FAST Fundamentals of Aerosecond Science and Technology. It's tutorial 1. Okay, one of the students asked a question regarding our favorite f of um, x minus vt form. When we went from f of x plus or minus v t to the differential equation, why did we choose the said function? The said function being the f of x minus v t or x plus v t form. F of x plus minus v t solves the wave equation, but why did we choose the second order? Can we find a first order equation as well, or could we have gone to higher orders? What is the why this particular equation is chosen to represent waves? Why did we choose trigonometric functions from an infinite catalog of functions that qualify? Why did we need to have a function that is periodic in space as well as in time? Okay, so that's a very relevant question for today's class, right? So, first of all, the reason why we chose a function of the form f of x plus or minus v t, the significance of the sign before v. So, what is v? V is the magnitude of the velocity vector. Okay. So, velocity vector is v. So, we can say that v is the speed of the wave propagation, speed of wave propagation, right, but this is greater than 0 the way it is defined. So, there is no ambiguity about it being positive or negative, and the negative sign corresponds to here the fact that the wave travels in the direction of increasing x or x coordinate. Okay, we can figure all this out rather quickly. First of all, why did we have to choose the x plus or minus v t form? That is the first question. So, what is happening in a wave? Now, here we go from concept to mathematics. That is the whole point about this discussion. So, wave connotes propagation. Propagation of what? Propagation of anything real, it could even be a complex quantity, but it connotes the propagation of an amplitude. Okay. So, ripples on a pond. So, you have a pond, you have ripples, right, something. If you have the same pond, you maybe have like a very light piece of something, the liquid gets displaced up, the liquid can also get depressed down, and this bob moves up and down in time, it moves up and down, right. But then you also see something that is propagating literally from the center, where maybe you dropped a stone or something, and the wave spreads out. This is a typical notion of a wave propagating somewhere, a visual, an example where the phenomenon is visible to the eye, it is slow enough that the eye can capture the dynamics of the wave and so on and so forth. So, it is a good place to start with. We do not even need to suppose things like, oh, sound is a whatever material wave and all that. It was all something which was historically discovered, as you may be aware. So, it was discovered that sound is a material wave by essentially having a bell ring in a glass jar, which when evacuated did not transmit sound, right. So, one discovered that, oh, this must be something therefore propagating through air and so on, but then it is also a propagating phenomenon. So, the key word is propagation. How do I describe propagation? So, when we talk about propagation, we talk about some amplitude, okay, some shape which is located at in some form. In this case, let us track the maximum point of this pulse or whatever the amplitude corresponds to, okay, and take a snapshot of this wave, and at a time t1, this entire shape was centered at this point, all right. Then as time lapsed, so let us say your clock started, this was t1, and then time elapsed and you went to t2. So, true to the nature of the wave phenomenon, what do we expect? We expect that the entire structure has moved if it is a forward propagating wave propagating in the direction of increasing x. We expect that this structure, which was here centered at t1, has made a forward progress and has gone to t2 faithfully. Every point has made a forward translation. So, what this tells me is that if this is a faithful transfer of whatever it is, then the quantity which described this shape here which is the function f, this shape is the function f. You could well have had a different f, this could also have been some other f, say f prime, a different f. You could have had the f to be a triangular function, a sawtooth function, and any which. It could even have been maybe a person or something on the move, right. It could even be could have been a bird or something like that, right. They all, we can describe a lot of these as propagating phenomena, provided it fulfills this notion. All we are saying is that if the shape of the amplitude at time t1, a snapshot of the amplitude across different points in space, and this one dimensional consideration was function f, it should retain the same function. If it is a wave propagating, then it should have retained the same shape as it moved from an object, a shape that was centered at t1 to an object which is after time lapsing from t1 to t2, it should have retained the same shape, but now centered at t2, and so on and so forth. Okay. So, what then has happened? You have shifted this entire thing, entire function f of x has gone from f of x from where it is to being f of x at another location, right. Oh, sorry, I should not have written t1 here. This is t1, it's not centered at t1, it is centered at some x naught, and now it is centered at some x naught plus a. So, the function has moved forward from whatever was centered at x naught to something that was the same thing now centered at x naught plus a. Now, if the propagation is faithful or high fidelity, whatever you want to call, it retains the same shape when being centered at x naught plus a as it did some time ago when it was centered at x naught. Therefore, what we now say is that whatever describes the wave being centered at f of x naught plus a, which where time has lapsed from t1 going to t2, the clock has ticked. Whatever be this function at the new center at t is equal to t2 is ably described by the same function, but now in its argument you subtract out the a, and in this case what is x? X is x naught plus an a, and the minus a comes forward at t is equal to t2. At t is equal to t2 also the form of the function turns out to be the same as it was when it was at t1, right. So, at t1 the function was something centered at x naught, at t2 also it became something centered at x naught. So, the trick is translation. Okay. So, this function should have, if I were to put it in more sophisticated terms, it should be invariant. It should not, the form, the shape of the function should not undergo any variance. It should be invariant when translated, that is, when it is moved from something centered at x naught to the same thing centered at x a. This is true for all of us, do not you think so? If I walk from here to the door and my face changes, it would really freak somebody out, isn't it? Vice versa. You do not want that to happen in real life. It would be stuff for the movies as it, but if it happens on a screen it is entertainment, if it happens in real life it is horror. So, that is the thing with wave propagation. So, we essentially need this mathematical description. Now, this tells you why the whole thing is linear in x and t in terms of the conceptual notion. Therefore, a general function f of x t, if it describes a wave and this physical phenomenon, then it must hold on to the form x minus v t. But we have gone beyond this in this course. All we have said the following: look, there should be an x minus v t f of x, a part of your complete description should be an f of x minus v t. You are even allowed to multiply this with some g of x or h of t. This slightly deviates, okay, this deviates from our primary notion of the function having to be just translationally invariant. Mixing or multiplying with these new functions g and x, it no more has the pure form of x minus v t. You have contaminated it with other functions, but in real life scenarios this may have to be the case. Okay. For example, we could have that the f of x t is e to the minus t by some t multiplying, let us give it some symbol, let us say g of x minus v t. So, what this tells me, even without much ado, I could immediately say that as time lapses and this wave propagates in time, it decays in amplitude. But isn't this what happens in a pond? So, you have ripples in a pond. So, you have a pond and you have ripples on it. We created this in the first place by throwing a rock. I know I am getting a bit too elementary maybe, but let us close with that. Nonetheless, you created some ripples and these ripples decay in time. You take a bell and strike it, the amplitude diminishes because, well, in the case of a bell, it is a very good example. It is an acoustic open resonator, open acoustic resonator. You stored some energy, it dissipated that energy, right. You strike a drum, it is a 2D resonator. Well, the resonator is not 2D, but it is a 2D membrane and the resonator beneath helps to sustain the oscillations longer, for example. But then you strike it once with an impulse and then it emits waves based on the resonances in the medium, but then this whole amplitude decays in time, right. The whole, sorry about that. Decays in time. So, a real wave would need further descriptions, okay. In the x minus v, f of x minus vt, you would typically have to multiply out with some other functions to keep things maybe real. Okay. So, that is one question. The other, why did you choose trigonometric functions? As we now see, the choice is dictated by the fact that is the beauty of the Fourier transform, right. You can a natural description of things would have dictated us to, would have asked us to consider other mathematical forms too. Okay, I think trigonometric is spelled like that. Why trigonometric? Because f of t, okay, in this case f of x t, any reasonable function, I must say, which has the form, in this case f of x minus v t. We could have chosen any function, but let us talk only about the time domain by fixing our attention to one point in space. So, that if we restrict our attention to x being x naught, and we can do this for any point x on the scale, right. So, then you essentially have this to be f of t, but if this function can be expressed using Fourier transform language as f of t to be minus infinity to infinity f of omega e to the I omega t, the integration happening over omega from minus infinity to infinity. Now, to get an idea of what this is, for every omega, although f tilde can have a complex value, I can plot its spectrum, right. What does this tell me? This tells me, or tells us rather, that you choose any omega, say omega 1, omega 2, omega 3, give me a frequency from 0 to infinity I will tell you how much contribution that frequency makes to this function, the function of interest, which is f of t. I can determine the amplitude. So, or in other words, I can decompose the function of my interest, which I described in the time domain as follows. I can decompose it to be essentially a okay, I probably do not get all of this right over a large number of cycles, or even a few cycles of these, few repetitions of these pulses, but you get the idea that we can express it as a sum of sinusoids. Okay. The sum is usually an infinite sum of sinusoids. As we will see going forward, or you probably learnt about it, you can basically take any f and classify these as periodic function versus an aperiodic function. If you were to decompose this in terms of Fouriers, then a periodic function would be described by a Fourier series, whereas this is a Fourier transform, whereas this is discrete, this is an integral. In other words, the spectrum of a periodic function is also periodic. Sorry, it needn't always be a line, but let me just draw it like that. The spectrum is also okay. Spectrum means omega, and this is S of omega, but this is what we discussed at great length in also an earlier discussion. Whereas in this case, if you had an aperiodic function, okay, its spectrum essentially turns out to be more concentrated, it is continuous. This is a concept which we will use quite a bit in this course. All right. Very well. So, let us move to the next question, but we are also kind of running out of time. What is the physical significance of phase delay? So, maybe I will just try and answer this at least in part. So, let us for this consider an example of the so called double slit experiment. You have a point source, it emits waves, and then you have a screen where you want to visualize this. So, you have a you have the point P, right. So, what does phase delay mean? Now, you have two sources, you went from source point S1 to S2. So, these two sources also emitted spherical wave fronts. Wave fronts are contours of equal phase, but then starting from the source point here, the wave propagated like this up to this point on the screen, and starting from this source point, the wave again cycled its way back to the screen. So, let us simply do this little exercise. Let us count how many cycles contributed from on the path S1P, and how many cycles did the wave make going from taking the path S2P. So, you have cycle 1, 2, 3, 4, 5, 6 cycles. Or 6 wavelengths, 6 spatial periods in this case. In this case, it is 1, 2, 3, 4, 5, 6, about 7. We have to be more exact than that, but what does this tell me? This tells me that there is a delay in time, or there is a difference in paths between path 1 and path 2. So, the difference in paths is 1 cycle, that is 6 minus 7, it is 1 wavelength, but 1 wavelength okay. So, this is E, 1 wavelength corresponds to how much of phase? The phase is essentially k, the propagation vector multiplied by whatever quantity in length you are interested in. So, if this is lambda, then k is 2 pi over lambda, and this, if this length is lambda, this corresponds to 2 pi radians in phase. So, now likewise I take this, the phase, the delay in phase, okay, the delay between path 2 which is longer and path 1 which is shorter, the delay turns out to be a lambda corresponding to 2 pi. So, this is essentially a path difference, we should prefix it with optical path difference, corresponds to a phase delay. So, delay usually connotes something in time, the flight or the train is delayed. That is because all phase is essentially you can mark any phase on a clock which begins at 0, goes over to pi over 2, goes over to pi, goes over to 3 pi over 2 and comes back to 0 or 2 pi. So, any delay, it could also have been 1 versus 100.1 cycles. It could have, we may have wanted to compare two paths which are like that. Okay, why not? I mean, in your resonator, right? For example, you had one the beam traversing once, it came back, it traversed again. You want to compare some delay between one round trip and maybe the 100th round trip. You can determine the phase delay, but then it will typically not turn out to be, in this case, 99.1 cycles. What does that even mean? So, you take each cycle is just 2 pi, right. So, whatever be the value for the phase, you can map this onto some phase point on this phase clock between 0 to 2 pi, and that is all that matters when you want to compare the interference between two waves, which is what is happening here. They are interfering. At point P. So, this is the physical significance of phase delay. So, a delay always has a reference. So, you have treat some piece of your wave as reference and the other as the thing which is to be compared with the reference. Okay. So, that is essentially what it is, but we will, I mean, if you are maybe concerned that, oh, this new jargon, new whatever thing, don't worry too much. We introduce this concept because we are going to use this concept, and the more we use, the more we will get familiar with it and say be reasonably confident about it, and actually further concepts will also be relying on this definition, and similar quantities would get defined. You have a phase delay, you also have a group delay, you have phase velocity, you have a group velocity. So, likewise these delays, it is going to be a game of delays in attosecond physics as well, right. So, therefore, it is very interesting, but keep all these notions in mind and they will come in handy as the course unfolds. Okay. So, with that, probably we should stop for today's class and tutorial and take it up. I will take up the remaining questions in the next tutorials to come. If they pile up a lot, I will maybe record a separate video to post a discussion about it, or perhaps write down things in order to explain these very important concepts. So, with that, I then say thanks for coming in today, especially those who are here in person, and we will meet in tomorrow's class.